Hello, welcome to our lesson on other applications of Extrema. So we know that we're applying the process of finding Extrema to problems involving optimization. And we saw this in our previous topic in the form of maximizing and minimizing things like costs and profits and revenues, business-related things. It's the same goal with today's lesson, it's just in different context. So in our optimization problems, we are still trying to maximize or minimize. So maximize or minimize, again, find an extrema, minimize. It's going to be maximizing or minimizing a particular value for a particular variable in our problem. And just as we saw in the previous applications, there could be lots of different variables. We have profit, we have revenue, we have cost, we have X as our unit being sold, number of units being sold or produced, P, little lowercase p as price. All those different variables could be involved, and we maximized or minimized one of them. Similarly here, just different types of problems that aren't necessarily business related. So the general strategy that we focused on in our previous topic, aside from the functions that we were looking at, was to, well, let's define our variables and possibly sketch out a picture. Is going to be a little more helpful here than it was in the previous topic because of the types of problems that we're going to see. And then we're going to try to write an equation, possibly two equations, because we need something to differentiate in order to maximize or minimize. Now, we may have two equations, so there's going to be some primary equation that involves the variable. That's the one we're going to differentiate and try to find the max or min of, but we may have to use a secondary equation in order to get that primary equation in terms of just two variables so that we can differentiate. And then we have our equations. We want to decide which variable it is that we're optimizing. And again, that could be max or min, kind of depending on the situation. And again, it will need to be an equation with just one other variable. So we need a function in terms of two variables, just like an x and a y, or whatever the variables are that we take the derivative of. And once we have that, and it incorporates the variable that we're trying to optimize, we're going to differentiate, find the critical numbers in order to figure out our extremum. And we want to be mindful of our domain. If we get an x value in our solving, that doesn't apply, it's not, possible to have a negative or something like that, then we want to make sure we exclude that from the possibilities. And we also want to make sure that we're answering the question that's being asked, make sure we're answering appropriately. So solving for x doesn't necessarily mean we're done. It could be that we're solving for a different variable in our problem. So let's look at a few examples, and hopefully we'll get you prepared for what you're going to see in your assignment. In this first one, we're going to be maximizing volume. So we have a manufacturer. The manufacturer wants to design an open box that has a square base and a surface area of 108 square inches. What dimensions are going to produce a box with the maximum volume? Okay, so we're trying to maximize volume. That's going to be the primary equation, and we're looking for the dimensions that are going to make that happen. Okay, now first let's go ahead and draw this out because we're looking at an open box. I can try to draw a box here that has a square base. Use my little draw tool. And don't mind me while I use my technology. Almost done. Oops, turn my pen back on, that would be helpful. Okay, so let's say this is our box, and this box, let's pretend, has a square base. That means that this dimension on the bottom here will be the same as the dimension on the bottom here, and it's going to have some height. We don't know what that is, but it doesn't necessarily have to be the same as the square base, so I'm going to call it h just to be different there. And this is an open box, so the top of the box here, open, I'm just going to shade that in so I don't forget. Okay, so let's look at the other information that's given to us. It says, we've got our picture now, we've got our open box, we've got our square base. It says that the surface area here is 108 square inches. So if I was going to find the surface area, that means the combined area of each of the surfaces. So there are 5 surfaces in this box. There's the bottom of the box, the square, and then there's the 4 rectangular sides. So if I was to write an equation for that surface area, let me change colors here, I would say that that surface area, again, the area of all of the surfaces, would be the area of the bottom plus the 4 sides there. If I found the area of the bottom and added the area of the 4 sides, I would have the total area of all of those surfaces. So in this case, the area of the bottom, well, that bottom is a square, base times height, x times x, that's just going to be an x squared. And then I have 4 of the sides, and each of the sides has a dimension of the bottom and then the height. So x times h 4 times, right? X times h, we're going to have that. So 4xh. Now in this one it says that surface area is going to be 108. So I'm going to say that x squared plus 4x plus h is going to be 108. Okay, so we've got the picture, the open box. We've got the surface area in there, but what we're trying to do is find the dimensions that are going to maximize the volume, which means I need to introduce another equation here. If I'm trying to maximize volume, I need to write a volume equation. So the volume for this 3-dimensional figure here, volume, like areas, length times width, volume just takes into account that 3rd dimension, which in this case would be the height. So the volume is the length times the width times the height, or in this case, x times h, which means our volume is going to be x squared times h. So that's what we want to try to maximize. That's the one we're going to try to differentiate and find the extremum of. Now when we do this, remember that equation needs to be in 2 variables. We can't have a v and x and h in there when we're differentiating, right? We're looking for maxes and mins on a graph, and the graph is of a function, and that function has to be in 2 variables. So this is the one we want to differentiate, right? This is because this has to be in 2 variables, it's the reason we are given more information. So we're going to use our secondary equation here to try to get this primary equation that we're maximizing into a function form of 2 variables. So what I want to do is get rid of one of these variables, and what I'm going to choose to get rid of is the height here. Then I'll have a volume equation in terms of x, which is one of the dimensions I'll be looking for. Now to get rid of height, what I'm going to do is solve this equation for h. So if I solve this equation for h, the first thing I would do is subtract over the x squared, so 108 minus x squared, and then divide both sides by 4x. So 108 minus x squared divided by 4x. And I'm going to go ahead and divide each of those terms by 4x. So 108 divided by 4 is going to be 27. So I'll have 27 over x minus there's going to be a 1/4. I can't divide that. One of the x's will reduce, so I'll say 1/4 x. Okay? Now that I have this solved for h, if h is equal to 27 over x minus 1/4 x, I can replace h in my primary equation with that expression. So I'm going to replace h with what it's equal to. So this h becomes 27 over x minus 1/4 x. Which means now my volume is x squared times, again, 27 over x minus 1/4 x. And if I go ahead and distribute in that x squared, when I multiply here, remember this is over 1 of the x's is going to cancel, so I'll have a 27x left, minus when I distribute that here, I'm going to have a 1/4 and an x to the 3rd power. So now I have my primary equation, my volume equation in terms of 2 variables, and now I'm ready to differentiate. So I'm going to find the derivative of this volume function. So v prime is going to be 27 minus 1/4 times 3 will be 3/4 x to the 2nd power. Now that I have this, I can find my critical numbers. So where is 27 minus 3/4 x squared? Where is that going to equal 0? Well, let me go ahead and add over the 3/4 x squared. Let me multiply both sides by 4/3 to get x squared alone. So 27 times 4/3. I probably didn't need a calculator for that, but let's go. 36 equal to x squared, and now take the square root of both sides. Now technically when I square root I get a positive and a negative 6, but this is where we want to be mindful of the fact that we're in an application problem here. Be mindful of the domain. Like -6 is not going to be a possibility for the length and width of the base of this box. So we're going to go with just the positive 6 as our x. Okay? So at x equals 6, since it's the only critical number there, we know that's going to be the one that produces our maximum, so I don't need to go through the interval and the testing. This will be where we have our maximum. And now I just need to figure out all of my dimensions. So I want all of the dimensions, make sure I answer the question properly here. If x is 6, that means my base is going to be 6 by 6. And then what does my height have to be? Well, I have an equation here that I can use to find my height. So somewhere, I'm going to scooch all this over because I'm running out of space, which is crazy because I left myself all kinds of space for this problem. Okay, so right now I know that my square base is going to be 6, what are these, square inches, so 6 inches by 6 inches. And the height is going to be, let's see, if I plug a 6 in for x here, 27 over 6 minus 1/4 times 6. That's going to be 20, I do not want to do that, 27, I just don't want to deal with the fractions, hopefully you don't mind, 1/4 times 6, and we end up with 3. So the height's going to be 3 inches. And now we have the dimensions that are going to produce that maximum volume. And if I wanted to know what that maximum volume is, I can go back into my volume function. It doesn't ask for this, but in case you were, the max volume would then have to be the dimensions, the 6 times the 6 times the 3. So 6 times 6 being 36, 36 times 3 being 108 would make that 108 inches cubed. So it doesn't ask for that, but we should be able to use our information to ask whatever question is, or to answer whatever question is asked. Okay, so there's one application, not a business application, more of a geometric application of using Extrema. Let's look at another. So in this case, we're going to minimize a sum. It says the product of two positive numbers is 288, and we want to find or minimize the sum of the second number and 2 times, twice the first. I can't read, sorry. I'm trying to multitask here. The product of two positive numbers is 288. Minimize the sum of the second number and twice the first number. So we're looking at two different numbers here. Just like in that last problem, I defined the dimensions I was looking for in my picture as x and h. I want to define my numbers here. Now I don't really have anything to draw out, so I'm just going to define my variables. I'm going to let x equal my first number, and I'm going to let y equal my second number. And then go back into my problem and see what information it's giving me. So first it says that the product of these two numbers is 288. So if I was writing the product of my two numbers, I would say that x times y is equal to 288. Now what we're trying to minimize is the sum of the second number and twice the first number. So the sum that we're looking at is the second number, which I called y, and twice the first number, which I called x. So that sum of the first number, or the second number and twice the first number, that's what I'm trying to minimize. So this is the one I want to differentiate and find the extrema for. But again, this primary equation needs to be in terms of two variables in order to do that. So I'm going to use this secondary equation to get rid of one of those variables. And I'm just arbitrarily choosing. You can get rid of whatever you want here, x or y, whatever is in that secondary equation. I'm just going to choose to get rid of y. So I'm going to solve this equation for y by dividing over the x. That means that y is equal to 288 divided by x. And then replace. If y is equal to 288 divided by x, then this y can be replaced with 288 divided by x. So when I rewrite my sum, it becomes, instead of y plus 2x, becomes 288 over x plus 2x. So this is the one I want to differentiate. So I'm going to take one more step and rewrite this as 288x to the negative first. And now finding my derivative will be pretty straightforward. So s prime would be negative 288 x to the negative second plus 2, and I want to find the critical number for this derivative. So that would be negative 288 over x squared plus 2. Where is that going to be equal? Equal to 0 or undefined. So let's see here. If I added, I'm going to go ahead and add the negative 288 over. If I add it over, it becomes a positive. Add it over to the other side, and then I have a proportion here that I can cross multiply to try and solve. So cross multiply here, that cross product is 288. That's going to equal 2 times x squared here. Dividing over the 2, I get 144, and then taking the square root of both sides, I technically get positive and negative 12. And here, because it says we're dealing with two positive numbers, means I'm not going to deal with that negative 12 as a possibility. So we're just going to go with x equals positive 12. So that's my first number. First number I called x is going to be positive 12. Then my second number I can figure out. Let's see, because I know that the product of these two has to be 288. So 288 divided by 12 means the other number is going to be 24. So my first number is 12, my second number is 24. That's all it asks for. Actually, it doesn't ask a single question in there. Minimize the sum. Okay, so it doesn't ask a question, but I probably should have typed one in there. The question should have been, find the two numbers that minimize the sum. And again, it doesn't ask for a question here, so maybe I should answer more questions if I asked you for what that minimum sum is. That minimum sum we would plug into our sum equation would be y, which was 24, plus 2 times x, so 2 times 12, which is another 24. That makes that minimum sum 48. Okay, my apologies for not actually asking a question in that problem. Okay, but there it is. So we had a geometric example here, we just have this numeric example, and now we're going to look at one where we're minimizing the distance between points. So we're finding the point on the graph of y equals 4 minus x squared that is closest to the point 0, 2. This is one where I think a sketch would be helpful. Anytime we can draw out anything that represents our situation, I think it helps wrap your brain around what's happening. So let's try to do that here. I actually know what the graph of 4 minus x squared looks like. That's our parent parabola. It's upside down and then it's shifted up 4. If you didn't know that, just put it in Desmos and sketch out your picture based on that. So the graph is going to look something like this. That's actually pretty terrible, but it's going to be an upside down parabola that's shifted up 4. So something like this. So there's going to be some point on that graph that is going to be closest to the point at 0, 2. So 0, 2, this point right here. So the question is, what point on the graph, so some point maybe like here-ish, and there's going to have to be a symmetrical point, right, because there's symmetry on the graph that will be the same distance away. One point on this graph is the closest to the point at, what point on this graph is the closest to that point at 0, 2? So the point that's here, again 0, 2, closest to, let's just call this point x, y. So what I want to do is minimize, because I want the closest point, minimize the distance between those 2 points, which means I'm going to have to use my distance formula. So if you remember, the distance formula comes directly from the Pythagorean theorem. If we subtract the distance between our x's, square those, subtract the distance between our y's and square those, and then take the square root, we will get the distance between those 2 points. So that distance formula, again, comes directly from Pythagorean theorem. Hopefully it looks vaguely familiar. I want to minimize the distance between these 2 points, which means I want this distance formula to be the thing that I'm minimizing, right? Differentiating and find critical numbers of. So first, let's plug in our points. So we have a point here at 0, 2, and a second point we're just generically calling x and y. So x2 minus x1 in this case. So this will be our x1, y1, this will be our x2, y2. So over here, we're going to, I don't feel like drawing this square root every time, so I'm just going to square the distance here so I don't have to worry about that square root, just move it over. x2 minus x1 is going to be x minus 0, that's going to be squared. y2 minus y1 is going to be y minus 2, that's going to get squared. So d squared is going to equal x minus 0 squared is just going to give us an x squared. And then y minus 2 squared, if I multiply y minus 2 by itself, that's going to give me a y squared, negative 2y is negative 4y, and then plus 4. So I have a y squared, negative 4y, and then plus 4. Okay, so again, this is the thing I'm trying to differentiate. It needs to be in terms of two variables, which is why I have a secondary equation here. If I know that y is equal to 4 minus x squared, then I can replace each of these y's with 4 minus x squared and get that function in terms of two variables. So we're going to say d squared, let me change colors here. Say now d squared is equal to x squared plus, instead of y being squared, it's going to be 4 minus x squared squared, minus 4 times instead of y, 4 minus x squared, and then plus 4. Now because I'm trying to take the derivative of this, I want to clean this thing up. So we're looking at x squared plus 4 minus x squared squared is going to get me 16. A negative 4x squared and negative 4x squared, so negative 8x squared, and then a positive x to the fourth. And then distributing here, that's a negative 16, and then a positive 4x squared, and then a plus 4 at the end. Okay, so let's see, clean up a little bit more. We got some like terms. We have an x to the fourth, and then I got a bunch of x squareds. So an x squared here, negative 8x squared here, positive 4x squared here. So 1 minus 8 would be negative 7, and negative 7 and positive 4 makes negative 3. So negative 3x squareds. And then 16 and negative 16 cancel, great. So then just a plus 4. All right, so here's my equation. Now remember, I'm trying to differentiate. I'm going to bring my square root back over. So if I have the square root of x to the fourth minus 3x squared plus 4, then I can rewrite that with a rational exponent. So I'm looking at x to the fourth minus 3x squared plus 4 all to the 1/2. Whew. Okay, so there's a lot of algebra here. We have not done any calculus work yet. That was all just to set up our equation to get it ready for differentiation. So now I'm ready to take my derivative. And just give myself a little bit more space. Don't mind me. Oh, don't mind me. Oh my gosh, 3 times is going to be a charm. Ready? Okay, so let's find the derivative. So let's say d prime. I'm going to use my power rule. So 1/2 comes out in front, right? So 1/2 times x to the fourth minus 3x squared plus 4 raised to the 1/2 minus 1 is 1/2 minus 2/2, so negative 1/2. And then that has to be multiplied by the derivative of the inside. So I have to multiply by 4x to the third minus 6x. So if I clean that up, on the top of the fraction, I'm going to have 4x cubed minus 6x. On the bottom of my fraction, I'm going to have my 2 and my square root of x to the fourth minus 3x squared plus 4. Okay, so where is my derivative going to be equal to 0 is going to be where is my numerator equal to 0. So next step would be where is 4x cubed minus 6x, where's that going to equal 0? Let me factor out a 2 and an x, which will leave me an x squared minus 3. So that's x equal to 0, and At x equals 0, we're going to be 2 units away. I don't think that's going to be the point we want to be. We can keep that in the picture for the moment, but let's go here. If x squared minus 3 has to equal 0, then x squared has to equal 3, which x is going to be then plus or minus radical 3. Okay, so we have an x value in the coordinates that we're looking at. And so let me deal with this point real quick here. At x equals 0, this would be the point on our graph. We would be at 0 and positive 4. The distance between these 2 points at 0, 2 and 0, 4 is 2 units. And the distance here being, let's see, from x equals 0 to x equals radical 3. Yeah, I don't think we're going to get 3 answers on this one. But, shoot. If all 3 of those were critical numbers... Okay, so let's do it. We're going to have 3 coordinates here, 3 points, and at these 3 points we will have the same possible closest distance to the point at 0, 2. So we have an x value of 0, an x value of radical 3, and an x value of negative radical 3, and now we just want to find the corresponding y values. Now here we're going to go into this function that's going to help us solve for y. Y is 4 minus x squared. Oh, I think this is going to kill the 0. So 4 minus x squared. If we have 0, 4 minus 0 squared, obviously that's just going to be 4. That's the point we already said, 0, 4 on that graph. And then radical 3 squared, I don't need a calculator for this. If I plug radical 3 in there for x, positive or negative radical 3, when I square it, I'm going to get 3. And 4 minus 3 is going to give me 1. So I get 1 here, and I get 1 here. Now these two make sense because of the symmetry in the graph. So there's going to be one of those points here, the other one on the negative side, and then there's a third point here. Apparently all 3 of those points are the same minimal distance away from our point at 0, 2. So we end up with 3 points that are equidistant, and each of those is the smallest possible distance between 0, 2 and any other point on the graph. Right? Like clearly if we were here, the distance between the 2 points would be growing larger the farther away you got from these points, right? So at those 3 points, we have the smallest possible distance away. So not just the 1 point, but all 3 of these points would be answers. Now I will say that when you're doing this in Canvas, I think you're only going to be looking for one solution, but it's possible if there were more than one. This would be a tough thing for me to ask you to input into Desmos, into Canvas. And so if you were entering this on your assignment, you're going to use the decimal approximations instead of the radicals, just to make it easier for me to make it grade. So radical 3 is going to be about 1.73-ish. So you could also say about 1.731 and negative 1.731. Okay, so the decimal approximations, if you ended up with a radical or a fraction or something that's needs to be approximated, then go ahead and do that. If it's a fraction, go ahead and put the exact fraction in there. Alright, so some serious algebra work on this one, but hopefully the work makes sense. The problems I gave you in your assignment are very aligned to these, with the exception of one. One makes you think a little, but if you get something wrong in the feedback, I'll throw in a picture there and give you some pretty good direction, so hopefully you'll be okay. But as always, if you need some extra help, have questions, then just reach out. Alright, until next time, take care.